There are a lot of things about the universe that I find it almost impossible to imagine. Well, actually impossible to imagine. One's just the size and scale of it. I mean, in the piece of the universe we can see, there are something like, roughly, 2 trillion galaxies. We haven't counted them all, but that's an estimate based on surveys of the local universe. 2 trillion, 2,000 billion galaxies. And each galaxy is, let's say, around the size of the Milky Way. Some are bigger, some are smaller, but the Milky Way has 400 billion stars in it. It takes light over 100,000 years to cross a galaxy. And there are 2 trillion of them in the piece of the universe we can see. And we're very sure that that piece that we can see is a small bit of what may be an infinite universe beyond. We don't know, actually. And I always say, don't get worried about that, because nobody can picture it. It is impossible to visualize the scale of the universe. So that's the first thing. I could then list a lot of more things, but we'll stop there for now. But just the size and scale of it, I think, is beyond imagination.
Often is the case with science questions. There's not complete agreement, but there is a theory with which most people agree, which is that it was made in an impact. So very early on in the life of the solar system, so let's say 4.5 billion years ago or so, we think that a planet about the size of Mars collided with the young Earth. And it's sort of a glancing blow, actually, which caused a lot of rubble to go out into space, formed momentarily a ring around the Earth, somewhat like the rings around Saturn, but then that ring very quickly coalesced into the Moon. So we think that the Moon is made of mainly bits of the Earth and also bits of this other planet that glanced off it about, I'm not sure of the exact date, I think it's something like 4.5 billion years ago. It's very, very early, very soon after the Earth formed. Well, so first of all, what happens in there? So let's say the ones, by the way, the supermassive ones at the hearts of galaxies, we don't really know how they form. It's one of the things that the Square Kilometre Array, which mainly north of Perth here in Australia, is going to look at the formation of the first stars and galaxies to try to understand how those enormous things, many millions of times the mass of the sun, get into the centre of galaxies. But the smaller ones, the little ones, let's say the ones we've seen collide, which are about 30 times the mass of the sun, the big ones we've seen to collide, those form by the collapse of massive stars. So what happens is a star is holding itself up against the pull of its own gravity, which is trying to squash it down because of the nuclear reactions in the core of the star. So because the star shines, and that produces a pressure, if you like, that holds the thing up. But it can't keep burning its fuel forever, and when it runs out, gravity will take over again. And in the case of the most massive stars, then no known physical process can stop the collapse. So gravity wins. So it just collapses and collapses and collapses. As far as we know, forever. So you get an infinitely dense point of what, I can't even call it matter. It's gone, really. All there is left is the gravity in some sense. Now, we don't know whether that's true because we don't know the physics when these things get so dense and so tiny. We don't know what the physics is. So it may well not be just this infinitely dense point. We just don't know. So we give it a name, the singularity. But all that's left that you can observe in the universe is the gravity. All the matter is kind of gone into this. So it's one of the great questions in physics, and it's very strange. Strange things happen. For example, we can work out what the circumference of a black hole is. So we can go round the event horizon and say, well, it's so big. But if you say, what's the distance from the event horizon to the centre, it can be infinitely big as far as we can tell. So it's like a TARDIS in some sense inside a black hole. So we just don't really know. But it can be a lot, the radius can be a lot bigger than the circumference would suggest because of the curvature and bending of space and time. So they're really weird.
Well, is there anything beyond the universe? Probably not. We suspect quite strongly that our universe is it could well be infinite in extent, even our bit of the universe, even notwithstanding what I just said about this eternal inflation stuff. If we just take our universe, we're sure it exists far beyond the bit we can see. So why would I say that? Well, if you think about it, the universe, our bit at least, has been around for 13.8 billion years. That means that light has only had 13.8 billion years to travel from the bit that we can see to our eye. So we can only see as far as light has had time to travel. But we think there's a lot beyond that because of measurements we've made of how the universe is curved and what the structure of the universe is. So it undoubtedly extends beyond the little bubble that we can see. How far it extends, it's another great question. We don't know, but it could be infinite in extent. These are brilliant questions. It's one of the fundamental questions in modern theoretical physics. It's interesting, this idea of the Big Bang created the universe. That's what Einstein's theory says. That's textbook cosmology, if you like. But the current textbook picture is there was a phase in the universe's life before the Big Bang, if you define the Big Bang as the hot, dense phase from which the universe appeared to sort of burst forth 13.8 billion years ago. And that phase is called inflation. So what we think happened is that before that, the universe was accelerating exponentially fast. It means it was doubling and doubling and doubling in size. And the numbers are ridiculous. We think that if you started with a universe that was smaller than a single atom, then it would be bigger by a long way than the whole observable universe, with 350 billion galaxies in it, in less than a millionths of a second. For those of you that know scientific notation, it's something like 10 to the minus 35 or 10 to the minus 36 seconds. So a very rapid, exponentially fast expansion. And when that stopped, all the energy that was driving that expansion got dumped into space. It heated it up. It produced the particles of matter out of which we're made and all the things that we see out there in the sky. And that's what we see as the Big Bang. So that sounds fanciful, but that's standard cosmology at the moment. The big question then is, well, what started the inflation? What stopped the inflation? How long did the inflation go on for? And the answer to that is, we're not sure. We don't know. And I'll just say one last thing. Some of those theories suggest that the inflation doesn't stop all at once. It stops in patches. And every time it stops, you get a universe. And so some of these theories, they're called eternal inflation theories, suggest that there might not be just our universe, the bit that we can see, but there might be many universes, perhaps an infinite number of them, and they may be being produced all the time. So that's what to make of that, but that's where current modern cosmology is. Great question, don't know. However, we know it's there. We're absolutely sure now it's there from many different measurements, from the way that galaxies rotate, the way that galaxies interact with each other, and the whole evolution of the universe actually requires there to be dark matter, about 5 times as much dark matter as there is matter. So it completely outweighs the stuff out of which we are made, and all the stars we can see in the sky are made. So it doesn't glow. It's not stars, which is why it's called dark matter. What is it? It is, as a particle physicist, I would say it's probably, but that's an unscientific thing to say, but if I had to guess, it's a new kind of particle, I would guess. So a particle which we haven't discovered yet. There are theories, many theories in particle physics that suggest that there are other particles out there that are waiting to be discovered at places like the Large Hadron Collider. And so I think the evidence tends to suggest there should be some new kind of particle. And we may discover it. We have experiments in underground laboratories that are literally looking for the dark matter that we fly through as the Earth orbits around the Sun and the solar system goes around the galaxy and the galaxy passes through the universe. We're flying through this dark matter. So it does come through. It should be in this room now and in the room where you're sitting now, but it interacts very weakly with normal matter. So we have experiments looking for the very rare times when those dark matter particles might bump in to some matter. So we can look for it that way. Or we can try and make these new particles at particle accelerators like the Large Hadron Collider. So that would be my guess. It's a new kind of particle. I think everybody does. I think every scientist no scientist can picture that number. I mean, even the small number, 200 billion, which is the number of stars in one galaxy. And then when you say 2 trillion galaxies, that's, I challenge anyone to be able to picture that. But it is the reality that we've observed. We haven't counted all 2 trillion, by the way. We have a thing called the Sloan Digital Sky Survey, which maps the positions of galaxies. So you know how much of the sky you've surveyed, and you know how many galaxies you've counted, and then you can spread that across the wider universe, and you get this picture of a vast and possibly infinite universe. I mean, we know that the universe, or very strongly suspect that the universe is much bigger than the piece we can see. So we have good reason to think that's the case. Whether it's infinite or not is another question. And then that goes to your, can you picture infinity? Well, no one can picture infinity. There's a weird thing as well about, we say the universe began 13.8 billion years ago. So that's a measurement, because we can measure the speed that all the galaxies are flying away from us, essentially. And then you can run time backwards, if you like, to find out when they were all on top of each other. And so it's quite a simple measurement, and we've done that. So we say the universe began 13.8 billion years ago. But actually, all we know really was the universe was very hot and very dense at that time. And we have some theories that the universe was in existence before that, and perhaps some sort of circumstantial evidence. And that means that actually the universe could have always been there, eternal. And when I talk to people sometimes, some people get upset about that. Some people would rather it had a beginning. And the idea that it might have been around forever is more frightening somehow than the fact that it began. And it's interesting the way that people's minds work. What terrifies you the most, an eternal universe or a finite universe? Yeah, it could do. So those theories are back in vogue. Some of those theories are back in vogue again. So yes, some of them say that there's a cycling universe. So the Big Bang is an event when space gets very hot and very dense and filled with particles. And that may happen again. Or some of the other theories, there's a theory called eternal inflation, which is a theory that, and it's actually the most popular theory, I think, at the moment, for what happened, for why the Big Bang is the way that it is. Because it's got some very special features, the Big Bang, which we could talk about. But inflation is the idea that space-time was around before the Big Bang, and it was expanding extremely fast. And there was doubling in size in the most popular of these theories every 10 to the minus 37 seconds, which is 0.00000 with 37 noughts, 1 of a second. So it's an unimaginably fast expansion. And then the idea is that draws to a close, so it quite naturally sort of dies away and the expansion slows down. And all the energy that was causing that expansion sort of gets dumped into space and heats it up and makes particles, and that's what we call the Big Bang. And those theories, the slight extension to those, say that slowing down just happens in little patches. So most of the universe, the overwhelming majority of the universe, is still inflating at that insane sort of speed, and just little patches stop and they're Big Bangs. So you get multiple universes, a multiverse. It's called the inflationary multiverse, and we are in one of those bubbles, and that's one of the more popular theories. It's because light it's one of the strangest things in the universe, but one of the most useful, because it always travels at the same speed. Mm-hmm. It's what's called a constant of nature. Right. So no matter how the thing moves that emits the light, or how the thing's moving that's going to receive the light travels. There's a great book. I'm recommending a load of books now. There's a great book on relativity by Robert Garrosh. It's kind of an older book now, but he's one of the great experts. And he says in that book that light seems to care about space and time, right? The fabric of the universe. It doesn't care about what emitted it or what received it. It just goes along. It's a perfect measuring instrument, because it always travels at the same speed. It doesn't matter if the thing that emitted it is flying away from you at 99% the speed of light. If it emits light towards you, the light comes at the speed of light and goes past you. Wow. So that allows you to measure, it allows you to measure distances, which is why it's useful, because a light year is the distance light travels in a year. And if I said the distance a baseball travels in a year, you'd say, well, that's a stupid unit of measurement because how fast did you throw the baseball? But light travels at the same speed. So that's why it's useful. It's much more than that, though. Light, because it travels at the same speed, always, and nothing travels faster than light, it defines what's called the causal structure of the universe. So it tells us, if you have something that happens, can that something influence something else or not? Like, for example, if something happens and so anything that's, let's say there's a year light travel time. So anything that's further away than a light year for that time, within the space of a year, you can't communicate with it. It can't influence it. There can be no communication between the two because you'd have to go faster than light to get from that place to the other event. And so light plays a fundamental role in relativity. It's not only useful, it actually defines what's called the causal structure of the universe. And that's where you get into, which we might talk about, black holes and things, because they're regions of space from which even light can't escape. Is the study of the smallest building blocks of the universe and the forces that operate between them, and in particular the forces excluding gravity. So gravity doesn't come into particle physics at the moment. And it should do, we think, which is where black holes come in again, which we'll talk about in a bit. But at the moment, the reason is gravity is so weak as a force between particles that it's completely unmeasurable. But there are three other forces in the universe. There's the familiar one is electromagnetism, which is electricity, magnetism, fridge magnets, and so on. That's one force. And then there are two forces that operate in the atomic nucleus, called the weak and strong nuclear forces. And they're the things that stick the nucleus together and allow radioactive decay and so on. And so it's the study of those forces and the fundamental particles that interact through those forces that I would define as particle physics. I mean, if you think about what I mean by a force, by the way, it's the means by which things interact with each other in the universe. So we're sitting on a chair now or standing on the floor or something. There are forces acting. Why don't you fall through the chair? Right, there's something stopping you falling through the chair, and that's electromagnetism, actually. There are two bits to it. One bit is that there are electrons, which are negatively charged things, in the atoms in your chair, and like charges repel. So there's a force.
Wow.
And there's also, it should be said, a quantum mechanical effect, which is electrons don't like to be close to each other, which is called the exclusion principle. So you try and squash them closely, they repel each other, and they also try and avoid each other. And the combination of those is what makes stuff rigid, solid, right? So why is a brick wall solid? It's ultimately those effects. So it's forces. That's all there is. That's how you perceive the universe. It's why you stick together, right? So there's electromagnetism, which is a long-range force which is responsible for everything, actually, that we experience, other than gravity. But if you go into the atom, deep into the atom, there's an atomic nucleus, and the electrons go around the nucleus.
Yes.
And that nucleus is made of little things, protons and neutrons, but they're in turn made of things called quarks, which are the smallest things that we know of. Well, you have two up quarks and a down quark, roughly, in a proton, and two downs and an up in a neutron, right? So they make up the protons and neutrons. Those things are stuck together by something called the strong nuclear force, which is way stronger than electromagnetism at very short, but it doesn't leak out of the nucleus. It kind of fades away, and so you don't see it. You don't feel it. No. We don't really interact with it, other than it's holding our atomic nuclei together, so it's really important. And then the other one, the weak force, is something that allows protons to turn into neutrons. Wow. And that's really important, because what happens in the sun? So in the sun shines by taking hydrogen, which is protons, single protons, and building helium, which is the next simplest element. Helium nucleus is two protons and two neutrons. Right. So what has to happen is a proton has to turn into a neutron before it can stick together to make helium nuclei in the sun. And that's the weak nuclear force. So without that, the sun wouldn't shine, the stars wouldn't shine.
So the question is, we understand roughly how the universe evolved from a billionth of a second after it began. We understand how solar systems form. Indeed, we've seen many other solar systems forming. How did life begin? I started the talk by looking at the eye and the catfish, and we talked about us. How did that begin? It's another one of the big questions. The answer is we don't know. But again, this is an area that research is very active in now. So if you're interested in biology, rather than physics or chemistry or astronomy, biology is moving at an increasingly fast rate. And there are really strong, firm theories about how life began. Don't know for sure. One of the theories is that it may have begun about 3.8 billion years ago. We know that quite accurately, actually. So not long after the Earth formed, we see evidence of life appearing on Earth. One of the theories is it began deep below the oceans of Earth in what are called hydrothermal vents. So these are pictures of these vents, very, very deep. You're talking miles, kilometres below the ocean surface. And it's where little undersea volcanoes, essentially, from the heat from the Earth's core, driving up through the ocean floor to make these structures where you get super hot water, minerals, all sorts of things like carbon, all the things you need to make life are cooked almost in these environments. And one of the reasons that we think that life may have began deep below the ocean 3.8 billion years ago is, remarkably, in a way, these conditions are recreated in every cell in your bodies. So every cell in your body now, if you look at your finger, or you look at your arm, or you look at your friend sitting next to you, the cells in their bodies are doing some of the chemistry that we think occurred on the Earth 3.8 billion years ago. It's not the chemistry of the Earth today. The Earth was a very strange place 3.8 billion years ago. The oceans were very acidic. There was no oxygen in the atmosphere because there were no plants to put the oxygen into the atmosphere. And yet, in a way, our cells in our bodies are recreating those conditions. What's the answer? Well, the theory goes that that's because life began in those strange conditions all that time ago, and that's the way it's always done it. So it's almost right to say that when life left the vents, it put a bag around this chemistry and took it with it. And in a sense, you are that bag around the chemistry of the early Earth. Fascinating ideas, theories at the moment. But I just met a friend of mine, actually, I should say, at UCL the other day, at UCL in London, one of the universities in central London, who's built a little reactor. They built a little thing which is recreating these conditions as best as we can, as far as we know, to see what happens. Now, he's not expecting anything to crawl out of his test tube, but what he is expecting, possibly, is to see complex molecules, the molecules somewhat like the molecules that make up you and me, emerging from that little reactor. Very cutting-edge research, and over the years that's going to become more and more interesting. So I suspect that this area of biology, the origin of life, is going to get more and more interesting. More and more people are going to do it, and again, in 10 years' time, we're going to need biologists who are interested in the origins of life to go and explore that. It's a great question. It was if the universe is expanding, what does it expand into? The standard answer, as best we know at the moment, is that it doesn't expand into anything because it's space itself, and actually space-time, if you talk to Einstein, that's expanding. So it's not the right picture to think of a Big Bang in a pre-existing space, like imagine this room is the space and the Big Bang happens in the middle of the room. It's not like that at all. It seems that, as far as we know, space and time began at the Big Bang, and they've been stretching ever since. And so a kind of a related idea, it's very difficult to picture these ideas, but they're fun, right? Is where did the Big Bang happen? Right? You can imagine, you think, well, we're in this big box of a universe. Did it happen over there or over there or over there? It happened everywhere, because all the space that's here now in this room was made, as far as we know, at the Big Bang. So the Big Bang happened everywhere. So it's not expanding into anything. It's very difficult to picture that. What I should say is that the theory that deals with this, the underpinning, it's called Einstein's theory of general relativity. He wrote it down in 1915, and it's still our best theory of space and time, and the theory upon which all these interesting and strange ideas rest. And you learn that. It's quite tricky because it's all about curved space, but you learn it in a physics degree. So if you do a physics degree, you start learning about these ideas. It's just you learn about them because the maths is a bit hard, to be frank, because it's all about curvy space. What's that Doctor Who, isn't it? Curvy, wiggly, wobbly, spacey, timey. That's what it. That's it, basically. So it's a great question.
Well, we almost can. It's not the Webb telescope. There's something called the cosmic microwave background radiation, which is light that was emitted in the universe, and it's a very precise number. It's 380,000 years after the Big Bang, which is not very long at all. Right? The universe is 13.8 billion years old. So we can see that. It's microwaves because it's been stretched so much by the expansion of the universe. Going back, the problem with light is that in those earliest times, the universe was so hot and so dense that light couldn't travel through it. So it was opaque. So you can't use light to go back earlier than that. But what we can potentially do, not yet, we're not good enough yet, but the technology we use now to detect colliding black holes, which is another remarkable thing, but I'll leave that one aside for now. But we have the technology to do that. And that technology possibly could allow us to probe right back to this thing, the Big Bang. And again, whether or not that's the origin of time, we can talk about as well.